Thank you very much, Omer and Jakob.
From now, we're running a bit late, but you'll have the full time.
Okay, thanks very much. I think I would prefer to defer questions until the discussion at the end, although of course, if my discussants realize that something is extremely unclear, then they should feel free to jump in, but general questions would be most effective, I think, at the end. So this is joint work with Eszter Kabos, who was a student in Oxford and is now helping to run the municipality of Budapest. So we're all familiar with the idea that when individuals learn not only from private sources, but also by observing the choices of previous decision makers, information may fail to be aggregated and incorrect herds may result. Now, the conventional wisdom about such settings would appear to be that relative to equilibrium outcomes, efficiency would be improved by greater reliance on private information and less on the choices of others. However, most analyses, because they're focused on the question of whether complete learning obtains asymptotically or not, most analyses are not ideally suited to providing a welfare analysis of individual decision rules. So there are three questions that we pose in this work. First, how can we develop a flexible framework for welfare analysis of individual decision rules under a variety of observation structures? Second, is the conventional wisdom correct in general? And third, stepping back, when and why do informational externalities arise? So our three contributions address each of these questions in turn. We answer the question of how can we develop a flexible welfare analysis by studying steady states of environments with observational learning. So we will be working with a model that is familiar in most respects. There's an underlying state of the world which is binary. Individuals choose binary actions and have access to continuously distributed private signals. We will assume that each agent observes with some noise, and we'll call this noise recording error, a finite set of predecessors' choices. And in a steady state of our economy, each agent will use the same decision rule to map their private signal and their observations into their choice. We can then characterize equilibrium steady states as fixed points. Individuals optimize, taking as given the common rule used by all their predecessors, and their optimum does in fact match the common rule used by the predecessors. In such an environment, in such a steady state environment, the planner's welfare objective becomes very simple: to maximize the expected payoff of an agent in steady state. We can then perform a welfare analysis of stationary decision rules, where we assume that the planner can use no more information than agents use in equilibrium. Our second contribution is to show that the conventional wisdom regarding the direction of inefficiencies in individual decision rules is at best incomplete. So we show that whether there exist welfare improving adjustments to decision rules and what form they take depends on the observation structure. In what I'll call our benchmark model, we show that there's no scope for the planner to improve welfare in a symmetric environment where each agent observes with noise the choice of only one predecessor. And we furthermore show that for some observed data, welfare may be raised by having the agents place less weight on their private information rather than more weight. Our third contribution is to identify two distinct informational externalities that determine the existence and the form of welfare improving adjustments to decision rules. And I want to spend a couple of minutes describing these externalities now. The first one, which is the more familiar of the two, is the dispersion effect. This stems from the fact that agents do not internalize the value of spreading their followers' posteriors. This externality is also present in the canonical whole history observed setting, But in our model, as you'll see, its implications for the form of welfare improving adjustments are richer. The second externality, which is novel, is that individual optimization may not coincide with maximization of followers' expected degree of confidence in the state indicated by the data. And I want to stress that this externality is absent in the canonical whole history observed setting. Okay, so I'll say a few quick words about related literature. I'll lay out the model and the key definitions of steady state and equilibrium steady state. I'll then spend some time presenting and explaining our benchmark result, namely that the equilibrium steady state is welfare optimal in a symmetric environment where each agent observes the choice of only one predecessor. And then in the remaining time, I will discuss the two distinct types of informational externalities that arise with more general observation structures and illustrate each of them in a case where they are the only externality present. Okay, so there are two main classes of related literature. The first is that which assumes that each agent observes the whole history when it's his turn to take an action and studies the existence of welfare. Asks the question of, do welfare improving adjustments to decision rules exist? And if so, what form do they take? And as I said on the previous slide, I want to stress that in these papers, because the assumption is that the whole history is observed, the only informational externality is the dispersion effect. The second class of related literature is those papers which develop steady state analyses with bounded observation windows. And we will be hearing another such paper from Nicolas in 2 days' time. So let me turn to the environment. There's a binary state of the world. It's either low or high, which is assumed to be unchanged over time. I'll assume that there's a symmetric, unless I say otherwise, that the prior on the state of the world is symmetric with respect to the two states. The two states are equally likely. Each agent before moving observes a private signal on the support 0,1 open interval. And in state omega, the signal has a conditional density F sub omega. The private signals are IID across agents, conditional on the underlying state. We'll assume strict MLRP, and we'll assume that the likelihood ratio is continuous in sigma, going off to infinity as sigma goes to 1 and to 0 as sigma goes to 0. So signals have unbounded precision. I want to stress the symmetry of the signal structure with respect to the two states. Formally, that assumption is captured by this equation. In words, seeing a value of the signal that's less than a half is exactly as strong a signal in favor of the low state as would be seeing a value of the signal equal to 1 minus sigma in favor of the high state. So here's a picture showing you an example of a symmetric signal structure satisfying MLRP. Because of the assumption that the signal structure is symmetric, there's a convenient reinterpretation. We can think about each agent's private information as consisting of two components: an indicated state, the low state if the value of the signal is less than a half and the high state otherwise, and a strength of the signal, which is how far away the signal is from a half. We're going to use the notation P, which is a number greater than or equal to half, to denote the strength of the signal towards the indicated state. So P will be sigma if sigma is bigger than a half, and P will be 1 minus sigma otherwise. And the symmetry of the signal structure means that the conditional distribution of the strength of the signal is the same whether the underlying state is low or high. Okay, so let me describe the environment. We'll assume that the environment is stationary. The underlying state, the signal structure, the number of agents acting per period, the strategy space, and the observation structure are all unchanged across periods. Time is discrete, starting at minus infinity, so that we can be in a steady state. Each agent, when it's his turn to move, chooses a binary action, chooses either yes or no. We'll assume agents are risk neutral. They receive a payoff of 1 if they choose action no when the state is low, or action yes when the state is high, and a payoff of 0 otherwise. So the payoff function is also symmetric with respect to the states. Each agent moves once, but a finite number of agents may move per period. And each agent receives information about the recorded choices of a finite set of predecessors. Okay, we're going to introduce what we call recording error to ensure that the state of the world in the steady state, in the equilibrium steady state, is not fully learned. That's to enable the welfare analysis to be non-trivial, because we want to study whether the planner could do better by adjusting the cutoffs that agents use in the equilibrium steady state in either direction. So specifically, with probability 1 minus theta, which is somewhere between 0 and 0.5, an agent's action is misrecorded. Yes is recorded as no, or no is recorded as yes. These recording errors are IID across agents and periods, and they're independent of the state and the action. Once an action is recorded, correctly or not, the recorded version, which we'll call the datum, remains unchanged. Every agent who observes a given predecessor's choice sees the same datum, and the probabilistic structure of this recording error is common knowledge. Now, I want to stress that recording error is, to our mind, the simplest friction that serves our purpose of enabling a non-trivial welfare analysis. Alternatively, we could have studied a model in which the state follows a stationary Markov process, flipping after each period with a probability 1 minus theta. Such a model would be more complex in general, but in our benchmark setting with one datum observed, it would be completely isomorphic to the model here. Okay, so given MLRP, cutoff strategies are optimal for the agent. So in particular, if the state indicated by the private signal is opposite to that indicated by the observed data, then there's a critical strength of the signal, call it P tilde, which will vary with the observed data, such that the agent will follow the observed data if their private signal is sufficiently weak, the strength of it less than P tilde, and will follow their private signal if it's sufficiently strong. Given that, the language that I'm going to use is as follows. When P tilde decreases, that means that the set of signal realizations that outweigh the observed data expands. And so when P tilde decreases, we'll say agents put more weight on their private signal and less weight on the history, less weight on the observed data. And the reverse, if P tilde increases. If P tilde increases, agents put more weight on the history and less on their private signal. So that's the language that I'm going to use. Okay, so we're ready now for the definitions of a steady state and an equilibrium steady state. Suppose all agents across all periods use the same strategy as a function of the observed data. For each underlying state and each common cutoff strategy, just call it P tilde of the data observed by the agents in period T follows a Markov process. So the for a common cutoff strategy, P tilde of data, the steady state of the economy is described by the stationary distributions of the two Markov processes, one for each underlying state. And in an equilibrium steady state, ESS of the economy, each agent's optimal strategy matches the conjectured common cutoff strategy of all predecessors. So with these definitions, we're then ready to talk about the planner's welfare objective, which takes a very simple form. The planner's objective is to maximize the probability in the steady state that each agent chooses correctly. We'll assume the planner chooses a common stationary decision rule for all agents, which depends only on the data observed by each agent. So in other words, we won't allow the planner to use any more information than the agents themselves have. The first question we will ask of any version of the model is the equilibrium steady state welfare optimal? And if not, what changes in cutoffs would generate local improvements? Or in other words, in which direction, if any, would the planner want to nudge the agents? And what I want to stress here is that the steady state approach transforms the planner's problem from a dynamic one to an effectively static one. And this is the virtue of the steady state approach. Okay, so we're ready now to present what we call the benchmark version of our model, in which there's a single agent acting in each period, and each agent observes only the recorded datum from the previous period. I will say that a decision rule is symmetric if it uses the same cutoff level of the strength of the signal, whether the observed datum is no or yes. And here's the result for the benchmark model. With a single agent per period, a 1-period window, for any probability of recording error, there's a unique equilibrium steady state, and in it, agents use a symmetric strategy. And furthermore, the equilibrium steady state decision rule is optimal for the planner among all stationary rules, whether symmetric or not. I don't have time to get into the mechanics of the model, but let me just briefly talk you through a picture before giving you the intuition. In an equilibrium steady state, each agent takes as given, the equilibrium steady state involves symmetric rules. So each agent takes as given the symmetric cutoff used by all predecessors. In any steady state where the decision rules of all predecessors are symmetric with respect to the two states, the datum no and the datum yes are equally informative. And the green curve in this picture shows you informativeness as the common cutoff of all predecessors varies between 1/2 and 1. The red curve in the picture shows you the informativeness of the private signal as the signal moves, as the strength of the signal moves from 1/2 to 1, and it's increasing strictly because of strict MLRP. An equilibrium steady state cutoff equates the informativeness of the datum, the history, and the informativeness of the signal when those two pieces of information disagree. So then an equilibrium steady state is the intersection between the red and the green curve. And what the picture shows you is that in this benchmark model, the steady state informativeness of the datum is maximal exactly at the intersection, exactly at the equilibrium steady state. So why is this? Well, to understand this, the whole of the first proposition, there are two things we need to understand. We need to understand why the equilibrium steady state is welfare optimal among all symmetric stationary rules. And then we need to understand why it's welfare optimal among all stationary rules. So let's focus on the case of symmetric stationary rules. With symmetric rules used by the agents, each agent's degree of confidence in steady state in the datum is going to be exactly the same whether the datum is no or yes. So for the planner, maximizing the steady state probability of a correct decision is equivalent to maximizing the steady state degree of an agent's confidence that the datum they see is correct. But each agent, in choosing their cutoff in their privately optimal way, is going to be maximizing their own probability of making a correct decision, and hence they're going to be maximizing the probability that the datum seen by the next agent is correct. So when agents use symmetric rules, the planner can't gain by distorting agents' rules away from the equilibrium. To understand why the equilibrium steady state is welfare optimal among all stationary rules, think about introducing a small amount of asymmetry into the agent's common strategy. that would then move the agent's, the follower's degree of confidence, or that would move the agent's degree of confidence in the new steady state. The degree of confidence in a yes signal would now differ, a yes datum would now differ from a no datum. However, because we start from an equilibrium steady state with a symmetric rule, spreading those degrees of confidence, spreading the posteriors, is not going to have a first order effect on welfare. And in fact, one can show that such a change would have a negative second order effect. So there's no gain to the planner from moving away from symmetric rules. In fact, this benchmark result generalizes to any environment, even with stochastic sampling, as long as a single datum of a predecessor is sampled. So for any number of agents choosing per period, and any stationary stochastic sampling rule that samples a single agent's datum from some previous period, the unique ESS is exactly the same as in the model that I just discussed, and that ESS decision rule remains optimal for the planner among all stationary rules. So this benchmark shows us that the conventional wisdom that says that agents should, to improve, welfare would be improved by agents weighting their private information more highly, is not general. And in particular, we've identified a very simple environment and observation structure where the equilibrium steady state, where equilibrium behavior is in fact welfare optimal. So I now want to turn to discussing the two distinct types of externalities, informational externalities, that we can identify using this modeling approach. As I said, we call them the dispersion effect and the mean effect. The dispersion effect represents the fact that agents do not internalize the value of spreading their followers' posterior degree of confidence. When the posterior degree of confidence that an agent holds varies with the realized data, spreading their posteriors is going to yield a first order benefit, other things equal, because of the agent's ability to adapt their cutoff to their degree of confidence in the data they see.
Meg, we have 5 minutes.
Okay, good. Thank you. But okay, good. And when I say other things equal, I mean holding fixed the expected posterior degree of confidence. So here's a simple example which illustrates the dispersion effect. Let's take the benchmark model and make one change to it. Let's modify the prior to make it be asymmetric. And in particular, the prior probability of the low state exceeds that of the high state. So now let me call the cutoff used by agents following observation of a yes datum P yes, and similarly P no when they see a no datum. Because of the asymmetry in the prior, now at the equilibrium steady state, the degree of confidence that an agent holds will be lower if they see a yes datum than a no datum. So the ESS cutoffs are going to satisfy this inequality. And the result is the following.
I don't know if you heard me before, but there's 5 minutes left.
I did. Thank you, Omer.
Sorry about that.
So with this asymmetric prior, we have the following result, which illustrates the pure dispersion effect. With one agent per period, a 1 period window, and an asymmetric prior, the planner can increase welfare by raising the cutoff following observation of a yes datum, or decreasing the cutoff following the observation of a no datum. So what I want to stress is that welfare is improved by having agents rely less on their private signal after they see a yes history, and more after they see a no. And the rationale behind both of these changes is they spread followers' posteriors. Okay, I want to devote the remainder of my time to discussing what we call the mean effect, which is the second type of externality, which is new to and hasn't been identified, at least using this language before. It represents the fact that individual optimization may not coincide with maximization of followers' expected degree of confidence in the state indicated by the data. whether these two goals coincide, so whether the externality is present or not, and if not, the consequences for welfare improving adjustments in decision rules depend on the observation structure. If only one agent's datum is observed, these goals do coincide, so this externality is not present. It's also not present in the canonical whole history observed setting, and I don't have the time to discuss it. What I want to stress is that this externality arises whenever an agent's generated datum will not necessarily become the decision indicated by the data for their followers. So suppose, to illustrate the pure mean effect, suppose we have 3 or more agents who are acting each period, and each of them observes only a common, potentially noisy, binary aggregate of the data generated in the previous period. So I'll model the noisy aggregation process as follows. If K out of the M data points generated by the previous cohort are no, gamma K denotes the probability that the aggregate observation about that cohort is no. I'm going to assume that this aggregation process is symmetric with respect to yes and no, and coupling that with the assumption that agents use symmetric decision rules, symmetric with respect to no and yes, each agent's degree of confidence is going to be the same whether they see a no aggregate or a yes aggregate. So there's no role for the other effect, no role for spreading followers posteriors. I want to contrast 2 different types of aggregation process for which the results about the direction of welfare improvement are going to be different.
We're
yep.
more or less at time.
Okay, so let me just, depending on how data are aggregated, depending on whether the aggregation process is like a majority aggregation, very sensitive to changes in the middle, or sensitive only to changes in the extreme, the direction of the welfare improving adjustment can either be that agents should weight their private information more, or they should weight their private information less. And the critical insight is that what agents should be doing more of to improve welfare is to condition on realization of others' data such that their own data will change the aggregate. Or in other words, this new effect arises whenever an individual's generated datum won't necessarily become the decision indicated by the data for followers, or in other words, whenever an individual's datum is not certain to be pivotal for what state followers believe more likely. And I will stop there.
Okay, thank you very much. Any questions? So,
there is one question on the chat.
Okay.
Yeah. Go ahead. I'll read it out. So
thank you.
The question is, would the optimality of ESS decision rule in the benchmark scenario fail to hold if agents observe datum from potentially different predecessors, e.g. each period there are multiple agents acting and each follower observes the datum of an IID sampled predecessor? Thank you.
The result would remain exactly the same.
Okay. So
yeah.
So if I'm interested in this variant that you said about having the state change according to some kind of maybe slow Markov process. Mm-hmm. So you expect the results to more or less be the same, but they would be harder to prove, or what is the?
So I know that for the benchmark model, for the benchmark model where without stochastic sampling, where you're observing last period's datum, the model is isomorphic, so of course the results are the same. For the version of the benchmark, quote unquote, with stochastic sampling of some single previous datum, the welfare result is the same. But of course, if you're potentially sampling 7 periods ago, what you see is less informative than if you sampled 1 period ago, if the state is following a Markov process. But because the benchmark result, my first proposition, is independent of how much recording error there is, the welfare result would continue to hold even in a version of the model where the state follows a Markov process. The state following a Markov process and allowing somebody to see a single datum from a long time ago means the datum is less informative, which corresponds to more recording error, but the welfare result holds regardless of the amount of recording error. Where the alternative model would get more complicated would be when we considered larger data sets, and that I haven't analyzed in detail.
So Mag, is there any sort of comparative static in terms of the equilibrium welfare with respect to the number of data that one could see?
So there will be, so that's a very good question, Xiaosheng. I don't know. I haven't, it may be possible to construct an example showing that when you move from one datum to two, what I didn't have time to say, sorry, I just need to preface the answer so it makes sense. If I had had time to illustrate the dispersion effect by looking at a model where agents observed the last two data points in sequence, I would have shown you that the equilibrium steady state is not welfare optimal there, okay? In contrast to the case where they observed the last one. So that comparison then says that it's not obvious that allowing agents to see two data points in sequence is strictly better than seeing one. And in fact, I don't have a counterexample that shows that two data points could do better. I haven't spent very much time, so it is conceivable, but I don't know the answer to that question. The comparative statics are much easier and much more natural in the version of the model where there's M per cohort from the last period, and you see an aggregate. I can get natural comparative statics there when you take away the noise in the aggregate. Mm-hmm. But I suspect you were thinking about the former setting, and because of the externalities, the result isn't obvious.
Mm-hmm. Thanks.
Sure.